Good day, everyone. First, I'd like to thank the conveners for the invitation to provide a keynote for this great session. As everyone else, however, I am missing the chance to see a live volcano and to enjoy Hawaiian life with many friends and colleagues. Life never ceases to amaze. So today I'd like to use some of our group's work to reflect about the feedback between theory and applications. And this is very much at the core of this session, which is dedicated to using a theory from the field of physical chemistry to understand very complex geochemical questions about element cycling. And because of the theoretical nature of thermodynamics and kinetics, it is sometimes possible to forget that most of us are geologists. By definition, we like rocks. Fascination with rocks and minerals is why I chose a career in earth sciences. And on the right here is a much younger version of myself panning for gold in the Swiss Voralps. As much as finding gold is awesome, the main fascination is about how did this gold actually get there. Many of the gold grains that I found at the time had a silver color because of alloying with mercury. So this raises an amazing question. How are the cycling of these two very different elements actually connected? Today, much of the research in my group is dedicated to ore deposits, and mineral resources, of course, have huge economic significance. But how we resource our future carbon-free lifestyle is one of the really big questions of our time. But for me, however, ore deposits are natural monuments that demonstrate the grand scale and the magic of element cycling in our planet. What crazy chemistry, for example, did result in the formation of this assemblage of antimony, arsenic, and fluorine mineral in a pretty boring small manganese mine in the Swiss Alps. So because field geology very much brought me into the field, I will start with this assessment that theory is actually useless. And what better place to demonstrate that theory is indeed overrated than fluid rock interaction. For example, equilibrium thermodynamics predicts the congruent dissolution of salt in water. That is, sodium and chloride ions leave the surface of the sodium chloride crystal and react with water to form hydrated sodium and chloride ions. When we tried the same trick with a poorly soluble compound, namely the gold telluride calaverite, something very different happened. The most soluble component, that is tellurium, was leached out, leaving behind metallic gold. Zooming in, we can see that this metallic gold has a unique fibrous habit and also a microporous texture. This is not something that equilibrium thermodynamics could have predicted. Now, this raises an important question. Under some conditions, we observe indeed congruent dissolution, whereas in others, we don't. So how can we predict when our equilibrium thermodynamics predictions are correct? Let us start with a complex reaction involving an aluminosilicate mineral that actually behaves as expected. Feldspars are the most abundant minerals in the crust, and sanidine is a mixed sodium-potassium feldspar. Simple thermodynamics predicts congruent dissolution of sanidine in pure water, but recrystallization into two different feldspars in a sodium-rich solution. So the original sanidine is going to break down into a potassium-rich and a sodium-rich composition. The same happens irrespective if you have sodium chloride or sodium fluoride solutions. The lovely experiments of Norberg and co-authors in 2013 produced coexisting albite and K-feldspar as expected. When GAN did the same experiment in sodium fluoride rather than sodium chloride solution, she obtained very different results. At first, it appeared that nothing happened, aside from a small amount of albite forming atoll-like rims inside the sanidine. Chemical maps, however, reveal that the original cyanidine was replaced by a potassium-rich feldspar, with albite being a relic mineral occurring only at the reaction interface. This suggests that albite formed first and then was replaced by a potassium-rich feldspar. In other words, we observe sequential precipitation of a sodium-rich followed by a potassium-rich feldspar, rather than the coexistence of both feldspars as predicted by thermodynamics. We hypothesized that the presence of fluorine affected the nucleation of the feldspar. What this means for the often observed sodic alteration followed by potassium alteration in nature remains very much an open question. These few examples show that the theory often fails to predict fluid-rock interaction because kinetics is important in many of those reactions, and theory is just not mature enough to predict nucleation and growth at the mineral interface. An interesting observation, though, is that the final products are often at thermodynamic equilibrium, though they are different from the products predicted by models based purely on equilibrium. In terms of thermodynamics of hydrothermal fluids, what we know is derived from a relatively small number of experiments conducted over a limited range in pressure and temperatures. And because of that, the prediction of many models rely on extrapolations of these experimental properties to a broad range of conditions found in nature. Often these extrapolations are incredibly accurate, but sometimes they do fail. Uranyl complexing seems to provide us with a lovely example of failure of the extrapolation algorithm. Uranyl carbonate complexes are important for uranium transport at room temperature, but no high-temperature data are available. This diagram shows the logarithm of the concentration of uranium as a function of logarithm of concentration of bicarbonate in solution. Extrapolation of room temperature properties of uranyl carbonate complexes indicate high solubility of uranium in these carbonate-rich solutions. However, the new solubility data obtained by Alexander Kalintsev suggests that carbonate complexes are not significant at 200 degrees C. That is, the uranium concentrations are low no matter the amount of bicarbonate in those experimental data. So, why does temperature extrapolation fail sometimes? I believe that the main reason for that is that not all aqueous species are created equal. In particular, our models sometimes fail to account for changes in coordination, that is the geometry of the complexes, as a function of pressure and temperature. The first part of his talk has highlighted the importance of experiments because our theory are still limited and fail fairly often. However, theory is also awesome. Zinc complexing in chloride brines provides a great example of the power of theory. Zinc chloride complexes are responsible for zinc transport in most hydrothermal fluids. Therefore, a few high-quality studies have measured zinc solubility over a wide range of conditions. The plots on the left here show some of this experimental data as red circles, together with the predictions of the thermodynamic models provided by the different authors. You can see discrepancies of up to an order of magnitude in the predicted zinc concentrations. So what's wrong? There are two possible reasons for the discrepancies. Either some of the experiments are in error, or the thermodynamic model used by the different authors, and in particular the choice of zinc chloride complexes used to fit the experimental data, are not the correct ones. It should be noted that solubility data do not provide direct insights into the molecular structure of zinc chloride complexes, only information on the average zinc to chloride ratio in the complexes. Ab initio molecular dynamic simulations provide detailed insight into the nature and geometry of metal complexes. This simulation here started with an octahedral zinc aqua complex that is zinc surrounded by 6 water of hydration in octahedral manner. This is the main form of zinc in water at room temperature. However, this simulation is conducted at 200 degrees C, and here zinc quickly loses a couple of water of hydration, forming this tetrahedral aqua complex. But this doesn't last very long because one water is quickly replaced by a chloride ion. And then this ZnCl with a positive charge complex remains stable for the rest of the simulation. We can also use ab initio molecular dynamic simulations to measure the Gibbs free energy of complex forming reactions. And remember, this is purely theoretical. We need no experimental data to do that, except for benchmarking the choice of the potentials. In this case, the agreement at 200 degrees is not that bad. It's comparable to the differences between the different experimental studies. But the agreements at 350 degrees and 600 degrees is truly outstanding, reflecting better sampling of the configuration at the higher temperatures. These 3 diagrams show the differences in stability of zinc chloride complexes as a function of salinity and temperature, derived from 3 different sets of experiment. Our ab initio simulation identifies systematic errors in the previous interpretation, linked mainly to the coordination geometry of the zinc Cl3 complex. This complex is tetrahedral at lower temperature, but trigonal planar, that is anhydrous at higher temperature. This accounts for the surprising stability of this complex at higher temperature. And now, with such a reliable model, we can start thinking about what causes fractionation, for example, between zinc and cadmium in natural waters. There are some serious limitations in the use of ab initio molecular dynamics, as many systems are still too complex and only qualitative understanding is possible for these systems. So we need to choose our battles carefully. And I'd like to conclude by giving you a quick preview of the work that we are conducting on the pressure dependence of mineral solubility. A few years ago, Gleb Pokrovsky and his team performed a remarkable set of experiments showing that polysulfides, such as S3-, may be important sulfur species at high temperature and pressure. The measured free energies of formation of S3- are plotted in this diagram, and you can see that even at moderate pressures, error bars are quite large, reflecting the difficulty in performing these experiments. Here we will compare 2 different extrapolations to high pressure based on the same set of experiment and the same HKF model. The bottom set here was brought to my attention by Dmitry Sverdzenski. At low pressure, both interpretations agree perfectly. Even at 5 kilobar, it's very similar. However, as we go to 15 kilobar and 50 kilobar, the 2 interpretations deviate significantly. And this is basically a reflection of the different model of the molar volumes of the S3- ion. According to Sverdzenski, the molar volume at room temperature, 37.8 cubic centimeters per mole, decreases very rapidly as temperature and pressure increase to a value of about 13 or 12. In contrast, Sverdzenski assumed a very high molar volume for S3-, and this molar volume doesn't change very much with temperature and pressure staying above 70 cubic centimeters per mole. So this has a very large impact on the significance of the S3- ion down subduction zones. According to the model of Sverdzenski, only S3- is important in those fluids, whereas according to Sverdzenski, this is basically an irrelevant complex. We are developing a molecular dynamic-based method to measure the molar volume as a function of pressure and temperature. And this is important because we have so few experiments showing the change in molar volume with pressure for geologically relevant molecules. In the case of sulfur, S3- and sulfate have very different properties as ligand. The polysulfide ion, S3-, is a soft ligand that will bind with metals such as copper and gold, whereas sulfate is a hard ligand that can carry rare earth elements, for example. Hence, the speciation of sulfur has important applications to understanding mass transfer in the subduction zone, and in particular transfer of metals between the oceanic crust and the metasomatized mantle. So in conclusions, thank you very much for your attention. I hope to see you all very soon. Keep safe. And I hope that I have shown that we can like rocks and get really excited by our mixing up with mathematicians, physicists, and chemists to understand better our planet.